Alright, well, this is Dr. Bob, and today we're looking at some capacitors, charge, and potential. The reason why we want to talk about this is because it's related to the Space Telescope. And especially what's going on is that the Space Telescope has to use high voltages, and in order to use the high voltages, we have to be able to measure them. Now, this is going to be a way for us to do that. So let's take a look at how capacitors fit into the Space Telescope. But basically, the first thing we're going to talk about is some fundamental properties of capacitors in relation to charge and potential. In this video, capacitors in parallel, capacitors in series, and we're going to look at voltage dividers. The primary relationship between charge, potential, and capacitance, of course, is Q equals CV. And you can manipulate that equation. V is the voltage, Q is the charge, and C is the capacitance. C is also equal to Q over V. Of course, Q is charge in coulombs, C is capacitance in farads. P is the potential in voltage. Here's an example of capacitors in parallel. So you have over here Q1 plus Q1, which is charge on capacitor C1, and then Q1, of course, plus Q1 plus Q2. Actually, it should be the plus Q2. And this is charge on C2. Q3 is the charge on C3. Now Q3 is actually a measure of a number of electrons on the plates of the capacitors. So they collect up. So on one side you're going to get electrons, one side you're going to get basically holes. So on the positive side you're going to see holes. And then you'll see, or positive, yeah, you can see holes. And I'm trying to draw a plus sign here. Plus and minus charges. So electrons are going to be negative, holes are going to be positive. The total capacitance in this circuit is going to be just add up the capacitance of C1 plus C2 plus C3, and however many other capacitors you have here. You might have 100 or 1,000, or may just have 2 or 3 or 10. So when you add all those up, you get the total capacitance. The total charge is going to be, obviously, of course, Q1 plus Q2 plus Q3. This is Q2 by here. Plus Q3 on ad infinitum. Here is an example of capacitors in parallel. So C1 plus C2 plus C3, which is just, in this, you see we have C1 is 5 microfarad, C2 is 3 microfarad, and C3 is 2 microfarad. Just add those up, and you get the total capacitance of 10 microfarads. Total charge is, because we have 10 volts on this circuit, we have a charge on these capacitors. So in this case, it's Q1 plus Q2 plus Q3 is equal to basically the total capacitance times the voltage, which the total capacitance is 10 microfarads times 10 volts, and that gives us 100 microcoulombs. In series, it's a little bit different. Now here's an example of a series capacitance circuit. You have C1, C2, C3, and on into C sub n, however many, it might be 100, might be 10, might be 1 or 2. The charge is going to be the same on every capacitor. So plus Q minus Q plus Q minus Q plus Q minus Q, and so on. The total capacitance is 1 over the total is equal to 1 over C1 plus 1 over C2, 1 over C3, and so on, 1 over C sub n. So here's an example of capacitors in series, and we'll take a same 3 capacitors with 5 or 3 plus 2. Now, as with resistors in parallel, the total resistance or the total capacitance is going to be less than the lowest capacitor in the circuit. So let's look at this. C, 1 over C total, 1 over 5 plus 1 over 3 plus 1 over 2 microfarads. And what we get is going to be less than the 2, which is going to be 0.97 microfarads. So the next thing that this leads into, and one of the reasons we need this, it's going to be a capacitive voltage divider, and we'll talk about that in another video, is that we need to have some way of measuring the voltage drop. Let's say, for example, this is 20 kilovolts. We need to figure out 20,000 volts, and we want to be able to measure this without draining it. So anyway, we're going to use capacitors. In this case, we have an input voltage, which is just Vp minus Vn, and then over here you have Vp, Vn, and then you're measuring this at a center point between these capacitors, and that will give you basically a scaled output voltage. So Q1, which is this right here, it's equal C1 V drop. What I call V drop is Vp minus Vc. Q2 is C2 minus, or C2 times V out, and here's V out right here, Vc minus Vn, and of course Q1 is equal to Q2 because these voltages, these capacitors are in series. So both charges are the same. So what that says is that we can relate these two in an equation. Since these two are equal, then these two are equal. So let's look. C1 equals V, or C1 times V drop equals C2 times V out. And then when we rewrite this equation, V drop is just equal to C2 over C1 times V out. And then we're looking at the V input, which is this over here. V is equal to V drop plus V out. It's equal to these two. Rewrite that equation. V input, we know what V drop is equal to this, so we'll drop that in. C2 over C1 times V out plus V out. So when we're going to solve for V out, let's put our figure back in. V input, which is this one right here, is equal to V out times 1 plus C2 over C1. We'll rewrite this, C1 plus C2 over C1. And then V out is just equal to V input times C1 over C1 plus C2. Now, that looks a little bit odd because it's going to be same charge, but if this is a larger capacitor, it's going to have a lower voltage. Okay, so solving for V out, again, we have this. There's an example. Let's have 7 microfarads on top and 3 microfarads on bottom, and then V out will be just V out minus 0. Here we got V out equal to V input, which is 10 volts, times C1 over C1 plus C2, and then substitute these numbers in. We get V input equals 10 volts, we know that. C1 equals 7 microfarads, C2, so drop those into the equation. V out is equal to 10 over 10 divided by, or 7 divided by 10, and of course that comes out to V out equals to 7 volts. At this point we don't care too much about the Q, but it might be interesting to know what it is. Solve for Q1 and Q2. Notice that they're first off going to be the same. So Q equals CV. Q1 is going to be 7 times 3 volts, or 7 volts times 3 microfarad, and it takes out 21 microcoulombs. And then Q2 is going to be 3 volts times 7 microfarads, and also going to be the very same charge, 21 microcoulombs. Thanks for watching my program.